Hello everyone. In this video, we're going to talk about solving the first order ordinary with constant coefficient system of differential equations. And we will first part, we will take a look at whenever we have a distinct eigenvalues, this part. So and then we can move on to discuss about complex eigenvalues and the repeated eigenvalues. So the simplest one is whenever we have a distinct eigenvalues. So here we have a question and they're asked to find, to solve the system. So this matrix is A, which is a coefficient matrix, which is a constant, just consists of the constants. There is no any variable inside. So we want to solve this. First of all, we need to find the determinant of matrix A minus lambda I to be equal to 0. We want to find the eigenvalues. So we want to find this matrix. In order to find this matrix, we know the lambda is eigenvalue, which is a constant, and I is the identity matrix. So I will be 3 by 3 matrix because A is 3 by 3 matrix. So they need to be in the same size. Okay. Now, what will be A minus lambda I? Well, this determinant, we need to use these two lines. Then the inside will be 1 minus lambda. And then these entries will be the same. And this should be 2 minus lambda. This should be the same, and this should be the same, and also this should be 3 minus lambda. This should be equal to 0. So from here, we need to find the determinant of this matrix. I'm not going to fully explain it, but this will be 1 minus lambda times 2 minus lambda times 3 minus lambda minus 2. And then we will have minus 1 times 0 minus 2, which will be plus 2. And then plus 2 times 0 plus 2 minus lambda. Okay, this expression should be 0. Okay, if we simplify it, which is easy, we will get this part, 1 minus lambda times lambda minus 2 and lambda minus 3 will be equal to 0. So from here, one of the answers is 1, the other one is 2, and also 3. So we have our A matrix is 3 by 3, and we found 3 distinct eigenvalues. So at most, we can find 3 eigenvalues since the size of the matrix is 3 by 3. And we will find the eigenvectors corresponding to these eigenvalues, and they should also be independent. They must be independent, and we will see why. Okay, for lambda 1 equal to 1, we need to find the corresponding eigenvector. And for that one, we need to solve and plug in to the equation. A minus lambda 1 is 1, means I. And our eigen vector, and then 0. So we need to solve this. So if we put here our A matrix, and then this will be equal to 0 if we put 1. If we put 1 here, but remember this is determinant, so we need to convert it to the matrix. So if we put 1 here, it will be 0, and then the other entries will be the same. If we put 1 here, it will be 1, so it will be 1, then 2, 1, and 3 minus lambda, which is 3 minus 1 is 2. And then the other side is 0. And since this is a very simple matrix, I don't want to reduce to the row echelon matrix with the Gaussian eliminations. Rather, I can use directly our ordinary approach. So from here we can see b plus 2c is equal to 0. Again, b plus 2c is 0. And minus a plus b plus 2c equal to 0. What we notice from the first equation is 2c will be minus b. Then if we plug it here, this 2c will be minus b, right? And this b and b will cancel. And from here we can definitely say a equal to 0. And we know this expression as well. So for our a, b, c vector, a is definitely 0, b is minus 2c, and c is itself. So I wrote them all in terms of c. If we factor out the constant c, this will be 0, minus 2, 1. So this will be our eigenvector. I'm calling it v1. So we found for the lambda 1, which is eigenvalue, equal to 1, the corresponding eigenvector. We will do the same procedure and repeat it for all the other eigenvalues to find the corresponding eigenvectors. And I don't want to do the same procedures because they're easy. So we will find the eigenvector for the second one will be 1, 1, 0. And for eigenvalue 3, which is 3, the corresponding eigenvector will be 2, 2, 1. Now, the solution will be in what form? The solution is x of t, right? Since we want to find the x of t. So x of t will be in the form of c1 constant e to the lambda 1 t, and then eigenvector 1. And also the other ones as well. So they will be linear combination of these terms. Now if we plug them, our general solution will be c1 e to the t. What was v1? v1 was 0 minus 2, 1 plus C2 e to the 2t. V2 is 1, 1, 0 plus C3 e to the 3t 2, 2, 1. So this is the answer, and this is the final answer. If the question has given us the initial conditions, then we can easily find C1 and C2 and C3. Okay, this is another example for the system of differential equations with coefficient of constants. So in this example, we will see that the eigenvalues we will get are complex numbers. So as the same, we want to find a determinant of a minus lambda I equal to 0. So from here we can see that 1 minus lambda minus 5, 1 minus 3 minus lambda is going to be 0. And from here 1 minus lambda times minus 3 minus lambda minus plus 5 will be equal to 0. Okay, so from here, if we want to find lambda, lambda will be minus 1 plus minus I. So we found lambda as complex numbers. In this situation, each of these complex numbers have also conjugate numbers. For example, we can see we have two lambda, which they are the complex conjugate of each other. And in dealing with the solving these problems, just only one lambda, one of those conjugates is enough. And it will yield two eigenvectors. So solving just one is enough for us. So I'm considering minus 1 plus I, this eigenvalue. We want to find the we want to find and solve this expression. A minus, what is lambda? Lambda is this, minus 1 plus I. Then I, identity matrix equal to, then V equal to 0. Okay. Now, this will be equal to 2 minus I, minus 5, 1, minus 2, minus I, and the rest is 0. From here, how can we do? Well, we can again go with row echelon matrix forms, but since this matrix is very simple, I will use the equations. This is A and B, so we can say A is equal to 2 minus I, minus 5B equal to 0, and also A minus 2 minus I times B equal to 0. And this is also plus. From the bottom, we will realize that A equals to 2 plus I times B, or 2B plus IB. So if we want to draw our vector, A will be 2B plus IB, and B is itself. If you factor out B, which is a constant, then it will be 2 plus I1. So this will be our eigenvector. And as I said, the one eigenvalue is enough. It will yield two independent solutions. So let's remind ourselves what is the Euler's identity. Euler's identity is, for example, if this is, then this formula will be true. Okay, this is a very important formula that we're going to use. So what will be our answer? Well, for one specifically answer will be e to the, what was our lambda, minus 1 plus I times t times the eigenvector, which is 2 plus I1. Okay, I can write it as like this. And now I can expand this with Euler's identity formula. I can write it as cosine of t plus I sine t e to the minus t 2 plus I1. Now, what can I do? Well, I can expand it and distribute it to this part, so we will have okay, let me write it like this. Cosine of t 2 e to the minus t plus I e to the minus t. This is also 1 plus I sine of t 2 e to the minus t plus I e to the minus t, and this is also 1. So my goal is to differentiate, since we want the real valued solutions, we want to separate the imaginary parts and the real parts. So let's do this. This matrix will be equal to 2 e to the minus t cosine t plus I cosine t e to the minus t. Okay, and here will be cosine t plus I, no, I don't want to. I will put also I inside, so it will be 2 e to the 2I e to the minus t sine t. I times I will be minus 1 minus sine t e to the minus t, and then here we will have just I sine t. So now I want to separate the real part and imaginary part. So real part will be, we will have this expression 2 e to the minus t cosine t, and then we will have also this expression minus sine t e to the minus t, and in the denominator, in the second row, we will have cosine of t. This is the real part. And now the imaginary part, I'm moving I outside, so we will have cosine of t, this expression, cosine of t e to the minus t. And then this expression will be 2 e to the minus t sine t. And in the second row, we also have sine t. Okay. Now, this is the real part. This is the imaginary part. Okay, and they both give us the real valued solutions. So we want the linear combination of this. So if this real part is x1 and this imaginary part is x2, then the overall solution, the general solution, will be their linear combination. So it will be c1 x1 plus c2 x2. And of course, these are in function of t. So this is the answer. So the answer will be, if I, okay, let me see. I think I made a mistake. I didn't include this e to the minus t2 here, okay? So I need to add e to the minus t here and also e to the minus t here. Sorry. So we will have e to the minus t. Since I'm solving them right now. Okay. Now we can factor out e to the minus t to the outside. So it will be c1 e to the minus t 2 cosine t minus sine t cosine of t plus c2 e to the minus t and 2 sine t plus cosine of t and sine t. This is our answer. This is our answer. But remember, in the question, they gave us the initial values as well. So this is our initial value when x0 will yield 1, 1. So if we plug in t equal to 0 to our general solution, we will get that this will be 1, so it will be c1, and the above expression will be 2. The second row will be 1. Then this will be 0, and then 1 and 0. And this is equal to 1, 1. It is easy, and from here, we can clearly see that 2c1 plus c2 is equal to 1, and c1 will equal to 1. So from here as well, c2 will be minus 1. So we found it. With initial condition, our solution will be e to the minus t 2 cosine t minus sine t cosine of t minus e to the minus t to sine t plus cosine of t sine t. This is not our general solution, but our solution for this specific condition values. Okay, we're going to solve this question as well. In this question, we will see that we will encounter the repeated eigenvalues. So let's jump in and solve this question. First question says find the eigenvalues and corresponding eigenvectors and also the generalized eigenvectors of the coefficient matrix. So first step, we need to find determinant of A minus lambda I equal to 0. So from here, we will notice that we have this expression equal to 0. And we want to find lambda, which will be this expression equal to 0. And this one will be 1 minus lambda times minus lambda minus 0. So the overall, the overall expression will be 1 minus lambda times minus 1 lambda times lambda minus 0 equal to 0. So what we notice is that lambda for 1 and 2 will be 1, and also lambda 3 will be 0. So we have repeated roots here. As we can see, it's repeated 2 times. So remember that we want to find 3 eigenvectors which are independent. But from this one eigenvalue 1, we only can get one eigenvector. So we need another additional eigenvector, which is a generalized eigenvector, to get that, and then to solve the system. Okay, for eigenvalue 1, which is 1, we want to find A minus lambda is 1i, and the v1 equal to 0. So A minus I, what will be? It will be 0, 0, 0, 1, 0, 2, 5, 0, minus 1, 0, 0, 0. Okay. Now we're going to solve it with the same strategy. This is A, B, C. We can clearly see A plus 2C equal to 0, and 5A minus C equal to 0. From here, you can see A equals to minus 2C, and 5A equals to C. So this is not possible unless A and C both are equal to 0. We don't know about B. B can be anything, right? B can anything. So it is something like a free variable. So our vector ABC will be 0, 0, B. And we can factor out B, and it will be 0, 1, 0. So we can say this is our V1, our eigenvector. Now, the other thing is that our other eigenvalue, which is again 1, which is repeated, but we want to find the generalized eigenvector. So it will be in the form of the same A minus I, but we want to find v2 with the use of v1. So this will be 0, 0, 0, 1, 0, 2, again 5, 0, minus 1, but it will be in this form. Okay. So from here, again, A, B, C. A plus 2C is 1, and 5A minus C is equal to 0. So from here, we can clearly see 5A is equal to C. And if we plug it here for the 2C, it will be 11A equal to 1, right? So from here, we can see A is 1 over 11. So then C will be also 5 over 11. And B is also a free variable, right? B can take anything. So A, B, C will be 111. B can take anything. And C, 5 over 11. If we multiply both with 11, then it will be 1, 11b, and 5. Let's choose b to be 0, okay? So if b is 0, then it will be 1, 0, 5. This is our another eigenvector, which is v2. But it is generalized eigenvector. So the final one, which is itself a distinct eigenvector, which is 0. From here, again, I don't want to write it too much, but we will get the corresponding eigenvector as 0, minus 2, 1. So we found 3 eigenvectors which are independent. One of them is generalized eigenvector. And now part B, it says find the general solution of the given system. Remember, in this case, we will use a formula and we will use Jordan blocks or something like that. But I want to make it a little bit simpler. So we will have 3 set of solutions. And this linear combination of this set of solutions will be our answer, the general answer. The first set of solution, I'm calling it x1. Corresponding for lambda 1. Okay. And then x2 will be corresponding to lambda 2, which is again corresponding to lambda, which is again 1. But it is also has a term of generalized eigenvector v2. So its form will be e to the lambda 1t, and let's say v1. Okay. x2, sorry, I need to write it here. x2 will be in the form of t times e to the lambda 2t v1 plus e to the lambda 2 t v2. And x3 will be in the form of, which is not repeated eigenvalue, so it will be the same as x1. Okay. Remember, if we had 3 repeated the eigenvalue was repeated 3 times. Let me write it, for example, here, okay? Then it will be t squared over 2 factorial e to the lambda t v1 plus t to the 1 over 1 factorial e to the lambda t v of 2 plus e to the lambda t v 3. Okay, if we had 4, then these coefficients, as you can see, are in this form. It will start from first 1, then it will be times t. The coefficients which is multiplied to the e to the lambda t will be 1t. If we had 3, so as you saw, it would be like this. So if this is t to the 1 minus lambda, and this is obviously t to the 0 over 0 factorial, which is 1. So then this will go like this. Okay, which is the Taylor series of the function e to the t. Now, let's get back to the business and let's deal with this problem. So this was x2, now x3. Okay. Now, our fundamental of our matrix solution, which can be shown like this, will be, the column will be x1, the first column, the second x2, and the third one x3. And our general solution will be just these linear combinations. So it will be cx1, c1, c2 x2 plus c3 x3. And this is our final and general answers. Okay. Now in the question, part C says determine all possible initial conditions x0 such that for the solution xt of the corresponding initial value problem, limit of xt whenever t goes to infinity exists and is finite. So, okay. In part C, we just need to find the limit as t goes to infinity. Okay, find the limit of what? Limit of x of t as t goes to infinity. And in order to exist this equation, we will notice that c1 should be 0. Because if c1 is not equal to 0, then the expression will approach to the infinity. And also, and c2 is also should be equal to 0, because again, if you find these values, which I found here, which I'm showing them here, if we find these values and put them here, okay, in this expression, then these two constants should be 0, because then the expression will go to 0, but the C3 is not necessarily need to be anything. So here x0 will be just with be the C3 term, and 0 minus 2 1. Okay, so we found this, and and the question says that you need to find all the initial conditions. So the C3 also can be anything. So we found the questions and answered all of this. I hope these examples were quite good to solve the homogeneous system of ordinary differential equations. In 3 cases, when we had distinct eigenvalues, complex eigenvalues, and also the repeated eigenvalues. And thanks for watching.